Okay.
All right.
This meeting is being recorded.
Thanks. Yeah, so it's great to speak here. Thanks for the invitation. And today I'll be talking about multiplicative structures on Moore spectra. And so we start by saying, one of the fundamental differences between higher algebra and discrete algebra is the difficulties one encounters in taking quotients. In classical algebra, like, we can take z and we can take its quotient by 2, and that's just a perfectly reasonable thing for us to do. And so when we do that, we take the quotient of z by 2, this is a commutative algebra, and we don't encounter any difficulties. And somehow that's, what we learn about first, and so we never consider the possibility of difficulties until we come to things like the sphere spectrum, and we can try and take the quotient of the sphere spectrum by 2. And what we find is that this does not admit any unital multiplication. And so this it really throws a wrench in sort of trying to mimic a lot of the things we're used to in classical algebra and higher algebra because, well, there's not sort of a naive way to go to characteristic 2 where we have a perfect sphere, S module that is, also a ring that, is in characteristic 2. So let me just sketch through an argument of, why this thing isn't a ring. So let's switch back to black. Z mod 2 has a unique ring structure. So Z mod 2 has a unique ring structure. And so what that means is that if we did have a ring structure on S mod 2, then pi 0 of it would be Z mod 2 with its unique ring structure, so we get a ring map like that. And now what we're going to do is argue that this map, a ring map of this form is already a contradiction. So what we can do is we can look on F2 homology, and we would get a map of unital rings. I mean, I'm not assuming associative here. So on F2 homology, we would get a map. And that's going to go from, now I'm just going to use some notation, also denoted R. F2 adjoin E epsilon, so epsilon here is in degree 1, and it's exterior. And that's going to map to the dual Steenrod algebra. And so that's a polynomial algebra on theta 1, and then theta 2, and so on. And so right here we already have a problem, because if we consider the action of Steenrod squares, then what we have is that, square 1 of epsilon is 1 on this side. And so that forces that, R of epsilon has to be zeta 1 because we need to get something whose square 1 is 1 in the dual Steenrod algebra. But zeta 1 squared is not 0. And so we have a contradiction to this being, a map compatible with any sort of multiplication. But we didn't need, if S mod 2 had any multiplication, we would get such a thing, and so we're done. And so, we, already sort of the simplest sort of quotient we could try to take, there was just, a fundamental issue and no way to proceed. And so this sort of is the beginning of a whole lot of things from classical algebra that we don't have analogs for in higher algebra. And what this talk is going to be about is about, the closest we can get at the moment to, taking quotients. And so let me continue just looking at sort of spheres mod primes. So S mod 3 has a multiplication, but a similar argument shows that that multiplication can never be associative. And this is due to Toda from about 1968. And if we go to S mod P at P5 and above, Toda tells us that, S mod P is homotypically associative for P at least 5. However, it's not an E1 algebra. And so specifically, S mod P admits an AP-1 structure, A-1 algebra structure, but not any AP algebra structure. So we know exactly how much associativity we can put on a sphere mod prime. And this, is not stated outright, but it's due to Hockman and Prime. And the argument is essentially the same as the argument I sketched above, but, appropriately modified. So, now a natural question we might ask then to see if we can sort of improve the situation, because this is not very good. I mean, in AP algebra structure, you can do some things, but not so many. I mean, for example, you just don't have a well-behaved category of modules even. And so the question is, what happens if we look at powers of P? So, modding up by a power of a prime P. And, the main theorem I'm going to talk about today is this theorem of mine that says that S mod 8 emits an E1 algebra structure. S mod P squared emits an E1 algebra structure when P is an odd prime. S mod 2 to the Q is an EM algebra when Q is at least as large as 3 over 2 m plus 1. And S mod P to the Q is an EM algebra when Q is at least m plus 1, and here again, P is odd. And really, this theorem it flies in the face of sort of everything I was led to believe about how structured things can be, and it's just incredible to me that the proof ends up being as simple as it does. And, really, this theorem remotely can take quotients. And so I label that here today into it too much because it's, being the maximal generalization you can come up with, it's got a lot of parameters. So we have C, a stably EM monoidal category, and at least 2. And so what that means is we want the binary tensor product to commute with, to be exact separately in each variable. We have an object I in C and a map to the unit of C, V from I to C. And what we want to know is we want to assume that the cofiber of V, this 1 C mod V, emits a right unital multiplication. And once you have that data, then when you have n that is less than or equal to m, we have a tower of En algebras and En algebra maps, where we're taking the cofiber of the tensor powers of V. And so, in particular, you parse through all this, and you use, from back here, that S mod P has a right unital multiplication when P is at least 3, and you, in fact, get the 2 odd primary parts of theorem A. The even primary ones needs a slightly refined argument, but you would get a result from using that S mod 4 has a right unital multiplication. Okay. And so, I just want to pause before I jump into the proof of this theorem. That this theorem is quite general, and it really gives us a lot of quotients. In a lot of settings where we didn't have sort of small En algebras for n more than 1, we now do. We have, using this one, you can pretty quickly construct, generalized Smith-Toda spectra with En algebra structures where n is as large as you want it to be, just not infinity. You can just take quotients whenever you feel like it. It really makes the world a brighter place as far as I'm concerned. Okay. Now, in this talk, I'm just going to focus on S mod 8.
Excuse me, Robert, can I ask a question? Where is the M in that theorem?
The M is the level of monoidality of the background category.
C has an EM, E is in Mary,
Yep.
M is in Mary monoidal. Okay, thank you.
Yeah, so the idea is, if you want to take a quotient of a ring R, you want to imply this in the category of R modules. So if R is, EM plus 1, an EM plus 1 algebra, then it has an EM monoidal category of left modules. And so that's where that gets used. And that's why we want this less than symmetric monoidal on our background category, so we can take quotients of rings that aren't infinity. Okay, and so in this talk, I'm purely just going to focus on S mod 8, because somehow this is one of those proofs where, once you see one case of it, you could read the paper and you can kind of imagine that it generalizes nicely, but somehow the proof gets uglier in terms of bookkeeping, but you don't really need so many new ideas after you know how to do it for S mod 8. All right. Are there any questions this far?
I had a question. Do you know if any of these bounds are sharp, like they don't admit an EM+1 structure?
For this, like theorem B, I think it's within. For theorem B, it's within 1 or 2 of sharp. For theorem A, I don't know that any of them are sharp.
Okay, thank you.
You know, I tried, for example, to show that S mod 4 is not an E1 algebra. And I want to say I got as far as saying it is A8. And then I wasn't able to compute any further obstructions. So, you know, the sort of obstruction theory methods that I'm going to, like, be showcasing today they really don't want to give you anything more than this theorem says. But at the same time, you know, quotients of spheres by powers of primes are really special. And so just because the general theorem is sharp doesn't mean the special case is sharp. I mean, I find it tantalizing and also, you know, maybe it's a coincidence, maybe it's not, but these numbers here, this like m+1 and this 3/2 m+1, those kind of match up with the numbers you would see in like torsion bounds unstably. You know, and the 3/2 one that we see at prime 2, that's the best thing we have proven, but it's not conjectured to be sharp. And that m+1 it's really like 1 away from what's sharp. You know, if we're talking about torsion bounds, but somehow this like m+1 at odd primes and 3/2 m+1 at even primes is I don't have a connection other than the numerology there. Okay. Section 1. So obstruction theory and quotients. And so I'm going to start with just a broad question, which is how do we take quotients? And instead of answering in full generality, I'm just going to give, you know, one way we can do that. So one way to take a quotient is to reduce to a universal example. Well, it's only a somewhat of a universal example. And so what would that example be? It's, you have a sphere adjoining X in degree 0, and that's, you know, a polynomial algebra. And we can map that to a sphere by sending X to 0. And that's a quotient. And it, you know, it witnesses the sphere as the quotient of a polynomial algebra by the generator of polynomial algebra. That is a quotient by X. And so, given in E2 algebra R, if we have an E2 map that goes S adjoin X to R, which, you know, sends X to, you know, let's say some class Y and pi 0 of R, we can base change. All right, so this gives us S tensor over S adjoin X with R, let's move back to R mod Y, as an E1 algebra. And so there we have it, we have a quotient. That's, you know, our first quotient of the day. And so for the case of trying to mod out by 8, what we're going to do is we're going to try and use this strategy. So we're going to try and map in from a polynomial E1, the E2 algebra, and we're going to try and send X to 8. And so let me just make a remark here that so S, you know, the polynomial algebra on X is that's a free E1 algebra, but it's very far from being free as an E2 algebra. And so what that means is that it is, you know, substantially, you know, because it's a free E1 algebra, like we really do just get a map as soon as we say we want X to go to 8, we're good to go. But because it's not free, it's going to take some work at the E2 level. And the second remark here is, so over Q, you know, Q adjoin X is free as an E infinity algebra. And so what this says is that, you know, if we're working rationally, quotients are actually easy. And I'm not the first one to observe this, but it's worth pointing out that somehow this is really, you know, the heart of the difficulty of taking quotients is wrapped up in, you know, positive characteristic and power operations. And the lack of power operations rationally means this is not, you know, it's not really a hard, you know, a question so much. Okay, and so what do we want at this point? We want a map of E2 algebras, S adjoin X to a 2 complete sphere, and we want X map to 8. And as soon as we have that, we can base change and we'll be done. And so now let's let me take a step back here and review like a really general strategy we can try and make for making maps. So let's recall how obstruction theory works for spaces. And I mean this is like the simplest obstruction theory you would learn about in like in a first semester course on algebraic topology. So you might have a map of an inclusion of spaces A into X and a map from F from A to Z, and you might want to know when you can make an extension of this form. And so, a strategy would follow is you'd say, okay, we're going to, put a cell structure on X over A, and we're going to try and extend F over X one cell at a time. Okay. And now, each time we're trying to extend over a cell, we're going to run into an obstruction to making that extension. And so our obstructions lie in pi star z. And then the third piece here, which is really somehow the key one, is that the cells of X over A are measured by the relative homology of X and A. And so the point here is that, now we have this nice computable invariant, the relative homology, that tells us how many cells we need. And each of those cells gives us, we can try and extend over it, and we know where those obstructions cannot lie, and they're going to lie in certain homotropic groups of Z. Now, this is just like a really general pattern. And the theme of maybe the first section of this talk is that, this general pattern of you want to sort of have objects you think of as free or just cells, and if you know how something is built out of cells, then the obstructions just are coming from those attaching, how those cells are attached. And if you have a good homology theory, one that allows you to, that's both computable and measures what cells are used to build something, you can very quickly, make sort of a very lightweight obstruction theory in a lot of different contexts. So let me, phrase what we're trying to do in those terms. So the thing that's easy to do is I can take the free E2 algebra on a class X, and I can map that to a two-complete sphere by sending X to 8. And that's an E2 algebra map, and we're going to be working in the category of E2 algebras. And, it being free is why it makes it so easy to make this map. And, I have this polynomial E2 algebra, and I can send X to X, so I get a map like this. And so we have an extension problem. And I managed to write lifting problem when I should have said extension problem. But, and so we want to solve this extension problem and make our map. And now, the next thing is we need to measure the cells that are, the relative cells here. Now, cells for augmented E2 algebras are measured by the eCHT AQ. And now that's, sounds, quite complicated, but it does have a nice, pretty simple formula. And so this is computed by a double bar. This is computed by a double bar. And so if you're curious, I'll just say that the whole way of measuring cells for augmented EN algebras, falls into the header of causal duality and iterative bar constructions that do a duality between, EN algebras and EN coalgebras. But I'm going to keep things pretty low-tech today and just move forward from here. And so now we want to compute the cells of S adjoint X, so we need to compute the double bar of this thing. So we want to compute the bar of S adjoint X along the augmentation that sends X to 0. And so, well, that's by definition going to be the relative tensor product of a sphere over S adjoint X. And now, the relative tensor product of a quotient over itself is, one of these calculations you do about 1 million times in your life. And you're going to get S plus S1. And as an algebra, this is an exterior algebra. And so that, just, now this part's just notation. Angle brackets, epsilon, that's my notation for an exterior algebra. Okay, that's one bar down. And now let's do a second bar. Now we need to bar an exterior algebra. And now, what that is that? Well, when you borrow an exterior algebra, you tend to get a divided power algebra. And we don't care about the algebra structure, we just care about the underlying object. So let me just write that this ends up being, S0 plus S2 plus S4 plus S6 and so on. And now the trick to making these computations go through, because I'm kind of breeze through them and haven't justified a lot of steps, is if you make polynomial algebra as a graded E2 algebra, where X is in grading 1, then, for example, each of these spheres I get at this end stage here, the 0th one will be in grading 0, and the S2 will be in grading 1, and the S4 will be in grading 2. And because each cell is in its own separate grading, they can't be attached at all, so it just has to be a sum. And if I want to check that, in each grading we get one sphere, I can do that on like F2 homology, because if I see the F2 homology, these things are sort of, it's easy to see they're connective. And so at that point, you just need to know the F2 homology is rank 1, or the Z homology is rank 1. And so then that, by base change, that reduces us to actually taking the bar of, an exterior algebra in the most classical sense. Are there any questions at this point? Okay, then moving forward. So from this, by moving up the cells of, the E2 cells of a polynomial algebra one step at a time, we get a tower of E2 algebras, R0, R1, R2, and so on, where R0 is S1, or F is the sphere, S0. R1 is a free E2 algebra on the class X. And at each stage, you proceed from Rk minus 1 to Rk by taking a push out of E2 algebras over a free E2 algebra on a class Yk, where Yk is in degree 2k minus 3. And so, with that tower in hand, so if we suppose we had a map Rk minus 1 to the 2 complete sphere that sends x to 8, and what we want to do is we want to extend it to Rk. We want to make that extension. The obstruction is the image of that class Yk. And as soon as picking a null homotopy of Yk gives us such an extension. So we'll call the obstruction theta k. And that is going to be in pi 2k minus 3 to complete sphere. Okay. And as a remark, at odd primes, the first non-trivial class above degree 0 is alpha 1 in pi 2p minus 3. And what this says, or rather this is related to the fact that having an AP minus 1 structure on S mod P, that we had one. One can reformulate this so that each Yk is the obstruction to being AK, or maybe AK minus 1. But the numbers work out here such that, this vanishing gives you the AP minus 1 structure, and then alpha 1 in pi 2p minus 3 actually is the obstruction at looking at AP. Okay, so now we have our obstruction theory set up, we have a sequence of classes, and now we want to analyze those classes. And so we're on to section 2, deforming spectra. So the thing is pi 2k minus 3 of the 2 complete sphere is just generally non-zero. And so, we don't really know how to proceed, unless we really dig into it and learn how to compute these obstructions. So I'm going to try and dodge the issue by deforming the category of spectra, stating a related problem that reduces to the one that we want to know the answer to, and then finding that in this deformed context, the groups in which the obstructions lie are all 0. And so we don't have to know so much about what the obstructions are because they always end up living in 0 groups. So let's start to do that. So synthetic spectra over F2, as introduced by Piotr Strugowski, that is a one-parameter deformation of the category of spectra. With parameter tau. Okay, And let me just draw the kind of fundamental diagram, here. So we have synthetic spectra, and as a one-parameter deformation, there's two things we can do with it. We can set tau equals 1 and pass to the generic fiber, and that generic fiber is the category spectra. And we can set tau equals 0. When we set tau equals 0, we get sin F2, 0. And when we do that, we get the uncompleted derived category of Steiner comodules. And so, in this category, we have bigraded, and so, what this one-parameter deformation is recording is the atom spectral sequence. And so, stating again, what we're going to do is we're going to try to take the quotient by 8, but at each step we're going to remember what the Adams filtrations of the obstructions are, and we're going to find that we can make the obstructions live in such high Adams filtration that we automatically know they're 0 because they're just above the entire spectral sequence. So in synthetic spectra we have bigraded spheres, S, K, comma S, where K here is the topological degree and S is the Adams filtration. And as a note about the gradient conventions here, so if I take the simplicial suspension of S, that ends up being S1 comma minus 1. And so the upside of these, the K comma S gradient here is that K is the topological degree, that is a simple interpretation. S is Adams filtration, that is a simple interpretation. So both numbers have explicit meaning. The downside is whenever you have to do a simplicial suspension, you've got to modify two numbers. And so tau here is in 0 comma minus 1. And when you take pi star of x, so the bigraded homotopy groups of a synthetic spectrum X, you get a graded z-adjoint tau module, or a bigraded z-adjoint tau module. And it's worth recording here what happens in 0 comma star, right? So this is the degrees that contribute to pi 0, topological degree 0. And so you get, z, and then you adjoin class 2 tilde, and you also have your class tau, and you have this relation that 2 tilde tau equals 2. And so the point here is that what is 2 tilde doing? Well, 2 tilde is witnessing that 2 is divisible by tau, and that divisibility of tau is witnessing the fact that 2 is detected on the 1 line of the atom spectral sequence. There's a question in the chat. Let's see. Yeah, so let me elaborate on tau having Adams filtration minus 1. So to see that tau is supposed to have Adams filtration minus 1, you have to ask the question, what does multiplication by tau do? And so if I have a class, 2 tilde in degree 0 comma 1, what is that recording? That says that I have a witness to 2, 1 plus 1, having Adams filtration at least 1. If it was divisible by tau again, it would have Adams filtration at least 2, but 2 tilde is witnessing that 2 has Adams filtration at least 1. And when I multiply 2 tilde by tau, what I'm doing is I'm forgetting, one amount of how much Adams filtration it has. So 2 tilde times tau, I now have 2, which only remembers that it has Adams filtration at least 0. And so since a multiplication by tau is, decreasing your lower bound on the Adams filtration by 1, you're forgetting a little bit of your information, it naturally has Adams filtration minus 1. Okay. And so now, what we're going to try and do is we're going to try and quotient by 2 tilde cubed instead of 8. So 2 tilde cubed is in pi 0 comma 3 of the sphere. And now we're no longer taking quotients by things that are in exactly degree 0. And because we're no longer in exactly degree 0, we're going to need to consider some more general notions of polynomial algebras. And so let me elide the point here. So we do have, and we can construct a polynomial algebra, S adjoint X, where X has degree 0 comma 3. Okay, and so generalizing the previous computation of the cells of an E2 polynomial algebra in spectra, if we have an E2 polynomial algebra where our generator is in some hard degree L, where we have a level L, this guy will have E2 cells. The first one is L, that's the generator of the polynomial algebra, and the next cell is going to be a suspension 2 of the tensor square of L, And the third one is going to be suspension 4 of the tensor cube of L, and so on. And so that is just, the quick computation we need to do to figure out what bi-degrees our obstructions are in. So now at this point, we plug into that formula 0, 3 as our line bundle, and this leaves the obstructions, theta k, living in suspension 2k minus 3, s0, 3 to the k, mapping to the 2 tilde completion of the sphere. And these obstructions are for k greater than 2. And let me just, that's the homotopy class of maps, and let me just, rewrite this as a homotopy group. So this is pi 2k minus 3, comma k plus 3 of s 2 tilde completed. All right. And now what we're going to do is we're going to look at the homotopy groups of the sphere, and we're going to try and figure out where those obstructions live. So I have already, in blue here, circled 2 tilde cubed. And now let me just start filling in where this obstruction lives. So the first obstruction is right there. And the second one is in pi 3 and 5. And the third one is in pi 5 and 6. And the next one is here. And the next one is here. And so let me just, draw a dotted line through these. And so these are lying along the front line of slope 1/2. And in this chart, each dot is a z-adjoint tau module generator. And the red lines vertically are multiplication by 2 tilde. The horizontal ones are eta and nu multiplications. And I've purposefully truncated this chart at 12 so that I can avoid having any tau torsion in this range. And so already from this chart, what we can read off is that the groups where the first several obstructions lie are all 0, because multiplication by tau goes down 1. And so, here's theta 2, and that's 0 because it's in a 0 group. Here's theta 3, that's 0 because it's in a 0 group. Here's theta 4, that's 0 because it's in a 0 group. Here's theta 5, that's also 0 because it's in a 0 group. Somehow the notes I'm following... Yeah. And here's theta 6, and that's also 0 because it's in a 0 group. And now, what's great about this is that Adams in the late 50s, published in I think 1960, proved that the Adams vanishing line, which says that in X, so after modding out by tau, when k is greater than 0 and s is greater than 1/2 k plus 3/2, you just get 0. And then because the sphere is close enough to tau adequately complete, or the 2 tilde complete sphere is close enough, is tau adequately complete, what that means is that mod tau check implies that we just have vanishing for these groups. And so, we just have a line of slope 1/2 and another line of slope 1/2. They're parallel, and one of them has intercept about 2 greater than the other. And so everything just lies in 0 groups. And there it is. All the theta k's are in 0 groups. So we have an E2 algebra map. S adjoint X, the 2 complete sphere, or 2 tilde complete sphere, that sends X the 2 tilde cubed. There it is. Okay, and now, just at this point, I'm practically just reiterating things I've already said, but, if I tensor over S adjoint X with the map that sends X to 0 with, the 2 tilde complete sphere, then we get an E1 algebra structure on S mod 2 tilde cubed. There it is. There is a quotient by 2 tilde cubed. And now we can pass to the generic fiber. And when we pass to the generic fiber, we get an E2 algebra map, S adjoint X to the 2 complete sphere. And that's going to send X to 8. And, by taking that tensor product to pass to the quotient, we get an E1 algebra structure on S mod 8. There it is. And that's it. I'll maybe say a word about this, how you go about proving this general quotient lemma. The idea is that when you want to take a quotient, once you have enough of a ring structure to set up an atom spectral sequence based on that quotient, it has the nice feature that, the atom spectral sequence for the ring that you're taking the atom spectral sequence of is very, very simple. It's all on the 0 line. And when you're taking quotients by powers, it has a flat vanishing line on the E2 page if set up appropriately. And so, that when you do it that way, you can get the general quotient lemma, but somehow that's just, a whole lot more symbols on top of this basic argument that you want to look at the Adams filtration. Dan Eisen's asking, what happens with 2 tilde mod S mod 2 tilde squared or S mod 2 tilde? Yeah, so let me go up to this chart here. So in yellow, so let's start with, there's 2 tilde. And now, the formula for working out where theta 2 lives is you double the degree and then simplicity suspend once. Oh, my line is off by 1. That was the issue here. Sorry, guys. This line should be 1 higher than it is. Things are a little better than I... yes, you double the degree and go down right by 1. So 2 tilde, double it and go down. The obstruction lives in this degree. And that first obstruction, theta 2, is also Q1. And so for theta 2, the obstruction you get is, it ends up being eta. And it's just non-zero, and we're stuck. And that exactly corresponds to the fact that we couldn't put a multiplication on S mod 2. You can also see this when you take the tensor square of S mod 2, there's an eta from the top cell to the bottom cell, and this obstruction, this obstruction exactly identifies the top to bottom cell in the tensor square of the cofiber. That's what theta 2 does. Now, I don't have interpretations for theta 3 and above, or at least not, simple ones like that. But now I'm running out of colors, but I guess let's use greens for 2 tilde cubed. So we double the degree and descend off by 1. So the second one's here. And now the thing is that as we follow this formula, going to higher degrees, the slope is impacted by the power we used. So the Adams filtration of the class we started with, because we're taking multiples, impacts the slope. So for 2 tilde squared, you get classes that are on a flat line like this. And so the first one is in a 0 group, we're happy. The second one, eta cubed, is a potential obstruction. I don't remember my argument at the moment, but I remember I ruled that out. And so then you can proceed to the next one. But then you get to this one here that could be 4 times sigma, and I really have no idea how to rule that out. And I mean, if you get to the next one after that, this one here in stem 9, that one's somehow even harder to try to rule out. And so what's notable about this argument is somehow this line that shows up, as you move to higher and higher powers, not only does the intercept get better, the slope gets better too. And so somehow the number of degrees of wiggle room you have increases quite rapidly. And so that in particular even means that you can sort of get some sort of partial uniqueness. So if you have 1 extra degree of vanishing, you can say that the algebra you're constructing is unique up to homotopy, and if you've got 2 degrees of vanishing, you can say that it's unique up to a connected space of homotopies, but there's no contractible spaces straight up. So it's for the space of choices that are non-trivial. All right, well that's it. So thanks for inviting me. I hope everybody enjoyed my talk.